Hi, everyone. Thanks for having me. I am Rishabh Agarwal from Periodic Labs, and today I'm going to talk about what it takes to do reinforcement learning at the frontier, not on benchmarks, but on scientific problems with trillion parameter plus language models. Now, think of this as a practical guide, maybe some of the things we have learned. I'll talk about some of the things we have learned, and also, I guess, some of the infrastructure we have built to make reinforcement learning work at this kind of scale. All right, let's dive in. Um, yeah, so I guess before I start the talk, I would say like I believe that accelerating science is one of the most valuable use of AI. And the question is, are we actually directing the amount of compute towards accelerating science or advancing it, or are we mostly scaling RL on tasks such as let's say math and code, and hoping that science eventually will benefit? So at Periodic, we took a slightly different approach than others. So instead of waiting for, let's say, general purpose reasoning to trickle down, we asked what happens if we can just point reinforcement learning compute directly at, let's say, real scientific problems with experimental data serving as a way to come up, give us some sort of reward, right? And our core insight is actually very simple. So to create an AI scientist, uh, you actually have to do science. So progress has been basically historically fastest on verifiable environments. And in our setup, nature itself is the RL environment. So the AI agent, you can imagine, let's say the AI agent sits at the center, connected to, let's say, real physical laboratories, things like physics lab, chemistry lab. This supposedly proposes hypotheses, design experiments, and gets rewarded signal back from basically the actual experimental results. So the reward depends on the experiment it proposed and what happened in that. Uh, let's make it a bit more concrete. So like here, I'm just showing you the scientific method, nothing really new. You form an hypothesis, you run experiments, you collect observations, you then analyze these results, and then you refine the hypothesis. And this is basically a loop of what typically happens in most of the empirical sciences, and this is also true for the physical sciences. Now, there are two distinct bottlenecks in this loop. On the right-hand side, you see basically hypothesis generation and analysis of existing observations. Actually, you are bottlenecked by intelligence. And this is where large language models and reasoning models can come and help a lot. Uh, and I think this is where I think AI actually has the most promise. But there's an equally important bottleneck on the left-hand side, which is actually running experiments. Now, doing so might be cheap in certain domains and much more expensive in others. For example, when you're in the physical sciences, you need high throughput autonomous laboratories that can execute experiments at least at some of the pace of what an AI agent wants to iterate. And without that, you have really like a brilliant reasoner, but nothing to reason about in some sense, right? Um, and I guess the key insight for us at Periodic is that intelligence alone is not necessary, sorry, intelligence alone is necessary, but it's not sufficient. So you don't create new scientific knowledge just by thinking really hard. You create it when ideas are tested against reality. And I suppose that's why at Periodic we're building both these sites, the AI scientists as well as the autonomous laboratories for them to operate in. Um, all right. So what does it look like in practice? So I guess on the left-hand side, you're seeing an image from an autonomous laboratory. This is actually the lab we have at in Menlo Park, where robotic systems can actually synthesize materials. And notice that this is not a simulation. This is also not some sort of benchmark. This is actually a real lab producing actual experimental data and trying to make new materials. And then here's the observation step, which is, I guess, what is also known as materials characterization. So basically here you're trying to figure out what actually happened in this synthesis or material synthesis. And one of the primary techniques we use is this thing called X-ray diffraction or XRD. You can see the diffractometer in the image here on the bottom. I guess I'm flying my cursor there. And a typical diffraction pattern produces, which is like the squiggly graphs that you can see on this plot that I'm hovering my cursor on. And basically, XRD is how you identify what phases or what crystal structures are present in the material that you have synthesized. It is basically a measurement of the underlying ground truth state of the world. So the lab makes a sample, the diffractometer measures it, And now you have real experimental data that tells you whether your synthesis, let's say, actually produced what you intended or not, or what kind of things happened in this synthesis. And then I guess one thing you need for analyzing this sort of data is this thing called phase identification, which is basically taking the diffraction patterns from the characterization step and then trying to analyze that to figure out what are actually the crystalline phases or the materials that were synthesized in this process. And this is where we actually start, because this is basically both an important bottleneck and weakly verifiable. So what you do is that you take a diffraction pattern from the instrument, search against the structured databases, and then the model predicts which crystalline phases are present and at what probabilities. And then you confirm this by complex tools, just let's say rate refinement, which is some sort of a physics-based predicting procedures that validates whether the predicted phases actually explain the observed pattern. Now, this is a really hard problem. A single diffraction pattern can contain overlapping peaks from multiple phases, and then the model needs to reason about crystal symmetry and peak positions and relative intensities, while accounting for, I guess, the instrument noise. This is also the task where we apply RL. The model gets better at phase identification by training on, let's say, lots and lots of these data from our lab, with the refinement step providing the actual, some sort of ground truth signal. And I guess there are a couple of reasons why we start at this analysis step. First, it's actually an important bottleneck. Today, this phase identification step is largely done manually with complex tools by expert crystallographers. If we want to run thousands of experiments autonomously, we need this step to be automated and reliable. And second, and this is critical from an ML perspective, this step is weakly verifiable. We can check whether the model's prediction against the observed XRD measurements from the characterization step. So for the rest of this talk, I'll focus on how we use RL to train models for this scientific analysis task and what we have learned along this way. There's, of course, the harder step of basically, let's say, hypothesis generation. Well, I'll talk a bit about that. All right, so what does it look like? So this is what happens when you scale reinforcement learning compute on real scientific tasks. And of course, underlying this plot is also the amount of data that we are using, which is produced by the lab. So what's remarkable here is that this curve looks a lot like the scaling curves you see for math and code reasoning. So in a sense, we can say that the reinforcement learning compute scaling works for science also, even when your reward signals comes from the data from a physical lab instead of some sort of unit tests. Now, more importantly, I guess there's no synthetic data here and not any textbook examples. These are using the actual measurements from the instruments from the lab, all with all the noise and the complexity that entails with that. So I think this is really a very cool result. Okay. Yeah. The other thing is, I guess, RL actually expand the underlying LLM's capabilities here. And this plot, so the plots here kind of show what RL is really doing. So the red lines here are the best of n performance, which is the best answer the model produces across multiple samples, and the black line is the mean. And you can see at the start of the training, the best of n is already around 63%, meaning the base model can produce correct answers. It just doesn't do that reliably. And as reinforcement learning progresses, the mean catches up to this where the best of n performance started. So RL is essentially making the model's average performance match what was its previously best case performance. But here's what's even more interesting. The best of n performance is also climbing, as you can see from these plots. RL isn't just concentrating probability on best known solutions, it's also expanding coverage, meaning it's teaching the model to solve problems it couldn't solve before at all. And I guess here's the same scaling chart I showed you, but with an additional reference point. So the dotted line here I added is the basically Kimi K2.6, which is one of the strongest open weights model available, run with the context line of 230K. Now, this was just released last week. And basically what I'm showing is that our previous RL runs with the worst open weights model already surpass Kimi K2.6 fairly early in our RL training. But what's exciting is that we just don't, that not the fact that we beat it, but basically the fact that now we can actually use this new model as a base for our future RL runs. So in a sense, the source community can provide us the base to start from, and the RL can actually further improve the ceiling on the kind of tasks we care about. All right. Uh, so this talk is more going to be about scaling RL at the frontier. And this is a bit of a cheeky slide before the technical section to capture some of the discourse around RL for LLMs right now. On the left, basically there's a simple intuition that if any change in the RL stack does better, then we should just do more of that. And if it does worse, we shouldn't do that more of it anymore. And I guess we reach the same conclusion on the right once we develop a deep understanding of how RL works or not. But in the middle, there's a lot of discourse on, let's say, Twitter and this general community around what should be doing. Everyone's debating, let's say, things like PPO versus GRPO versus DAPO, asymmetric clipping, whether you need like FP32 or like a lot of these other things, basically. And the truth is that the core algorithm is actually simple. It's actually the engineering to make it work reliably at scale with, let's say, trillion plus parameter models and messy data and all these things. And I guess this is what the rest of the talk is going to be about, like some of the practical lessons we have learned scaling RL. And more concretely, here's kind of some of the roadmap for this talk. So basically, I'm going to talk about not the data aspect of things, but more about, let's say, the stable RL infra for large MOEs, that's 1 trillion plus parameters, which K2 is, and what does it entail? So some of the things I will be touching on is things like train-inference discrepancy, as well as async RL, and easy to tune and stable algorithms. Before I get into our specific findings, let me set up the framework we use to think about RL scaling. And this comes from the Art of RL Scaling Reinforcement Learning Compute paper, which is, I guess, presented as an oral at this conference. So the key insight is that, like, I think RL training generally follows the sigmoidal scaling law if you're measuring things, bounded metrics, let's say like accuracy or rewards. And you can sort of fit that with this formula that you see on the slide, but you can also basically interpret there are like two important things going on, which is different design choices can affect the asymptotic ceiling that you reach for a given model and data. What is the ceiling you can reach, as well as how fast you reach that ceiling, which is the compute efficiency term. And that's basically so what we do is we generally use this framework to think about all of our RL runs, and it lets us predict whether more compute will help or whether we have hit a ceiling and need to change our approach in some sense. And I guess this is one of the main important findings from that paper, which is different recipes would have actually different ceilings as well as different efficiencies. So basically, if you pick the wrong recipe, you can train it as long as you want, but it may not reach the ceiling of some other correctly picked recipe. So basically, this is basically, you should think about not every recipe is equally good, and it's not just a matter of efficiency, but actually some changes might lead to a different ceiling itself. And one of the things that can really affect ceiling is this thing called train-inference mismatch in on-policy RL. So basically, let's say even if you're doing on-policy, meaning you're exactly using the same weights for inference and training, meaning you're generating rollouts using the same weights as well as training using these exact weights. This is still not exactly on policy. And then the reason is that you actually have two separate engines when doing any sort of RL for LLMs. You have the sampler, which is, let's say, things like VLM or SGLine are the typical sampler engines that we use, which generates the rollouts. And then you have the learner engine, which is things like, let's say, your Megatron, where we compute the policy gradient and the loss and compute the weight update so that we need to update the weights. And policy gradient typically assumes that these are the same model, that you're sampling actions from some policy and you're exactly updating that policy. But in reality, if you do on-policy RL with a fixed set of weights, you end up doing something like this, that where you're sampling from the sampler policy and you're training on the learner policy, even though they have the same underlying weights, there is a mismatch between the log probabilities or probabilities they assign to different tokens because of the fact that they use different kernels, maybe even different numerical precisions, and a bunch of other things. And these also have things in compound together. And I guess the scatter plot here shows you the mismatch, which is basically if you take a policy, and then you run it through the sampler and training engine, you expect that all the tokens would lie on this y equal to x line, which is basically all the tokens probabilities are exactly the same between the training and sampler engine. But you actually see a very visible spread. Um, some tokens have probability estimates that can even differ by, let's say, zero point 0.4, which is like pretty large diff in the probability difference. So inference and because yeah. So what happens is that there is an underlying mismatch in your training objective itself, even when we're doing on policy RL. And the thing is that this mismatch is actually worse for MOEs. And what happens is that if you train with this sort of mismatch, uh, generally what we see is that training works fine until it doesn't. So this is like the sort of effect we see often, that basically it's almost like a silent killer of your runs. Your RL runs would look really fine. And this is, by the way, for the plot here is shown for a large MOE by this paper, where they try to fix everything except they're just reducing the amount of mismatch between trainer and inference by actually fixing some of the discrepancy sources one by one. And you can see that once they fix enough of these sources, you get stable learning. And I guess this is what I mean by basically RL really wants to work for small LLMs because this mismatch is not that pronounced, but you actually have to make it work for larger MOEs. And let's say the models like QMK2 or the other frontier open weights models. All right. So one of the common things, or one of the tricks we do to mitigate this train inference discrepancy, is this thing called router replay. And what it does is basically in a mixture of experts model, the router decides which experts process each token. And the problem is that the inference engine and the training engine might route tokens to different experts, even with identical weights, due to the, let's say, the mismatch I just talked about. So the fix is basically simple. So during rollout, you actually record all these routing decisions, like which experts were selected for each which token. And then during training forward pass, instead of rerunning the router, you actually replay these saved decisions. And this guarantees the same experts are activated so that the log probabilities actually match. And basically what we see is that there is a substantial reduction in the expected sample size. Uh, Yeah, so there is, sorry, a substantial reduction in the expected sample size if we don't do this router replay thingy. But if once we add the router replay, we see the expected sample size, or ESS for short, actually improves. And generally, higher ESS is better. This is basically a diagnostic to tell how stable your learning is. And we see a sizable impact of doing something like this. Now, of course, router replay isn't free. There are multiple costs associated with this. The first one is infra complexity. You do need to plumb these routing decisions from the inference engine through to the training engine. And so this is like a non-trivial amount of systems engineering. And second is that there is an overhead because we are actually saving and replaying these decisions. So it adds cost both to the both training and inference. And basically, if you use the default implementation from VLM, then this actually causes you degrades your throughput much more, while our in-house implementation is about 60% faster. And this is done by optimizing how we capture as well as transfer this routing data. And here's a fun one. Sometimes the mismatch isn't even in your code. It's in the GPU kernels themselves. So one fun bug we discovered was actually when we wanted to do sequence packing, which is a very common optimization, so that rather than padding, you can actually train by packing multiple sequence so that you can utilize your max context length as much as possible and change your attention mass so that the training is still optimizing the same loss. So this is like what is shown on the right-hand side. Once we switched to that, we started seeing a much larger discrepancy between train and inference. And on digging further, what we found was that the causal and the padding causal kernels actually produce different attention outputs for the same inputs. So we typically use the causal kernel during the autoregressive generation. But during, if you're using sequence passing, then we use this thing called padding causal, and that actually has this huge mismatch. And apparently the mismatch was 4 times larger between these two kernels. So in terms of the KL divergence. So basically, you can see like sometimes you also run into when you're doing RL at the frontier, you can also run into these kind of kernel bugs that can actually create a huge amount of mismatch. The nice thing is, at least NVIDIA is currently working on an upstream fix for this thing so that everyone can use this. All right, so switching gears, the second major challenge in large-scale RL is that it has to be asynchronous. And what I mean by that is, let's say the default synchronous RL is actually very wasteful, where you basically alternate between generating and training. So you generate a bunch of rollouts, and then you basically train on these rollouts, and so on and so forth. And this process is actually very wasteful. And the reason is because, let's say the rollouts actually take a variable amount of times to finish, and your GPUs are basically waiting idle, or they're actually sitting idle for your longest rollout to finish. So you can see basically how wasteful this is. Like all the time that the longest rollout hasn't finished, the other GPUs are just sitting idle. Uh, Clearly, there is something better, and this better thing is called async RL, where we try to overlap some of the generation of the rollouts with the training, so there is not as much waiting time. Uh, so basically, what happens is as soon as a rollout is generated, it goes into a buffer while the training is trying to pull batches from that buffer. So you can generate, let's say, 2 batches worth of data, while the trainer starts working on this first batch. The generator is already trying to generate the second batch, which is what I'm showing here. Now, there's an even better way of doing async RL, which is called pipeline RL. And what we can do here is that rather than having some sort of trainer pulling data from a buffer and inference engine, because the thing is, if you go back to the default image, there is still some idle time, which is once the longest rollout time once, let's say we have finished generating almost all the rollouts except some of the longer runs, the GPUs are now sitting idle. Instead of that, what pipeline RL says is that basically inference runs continuously at a near constant batch size, which is as soon as your one rollout finishes, a new prompt immediately takes its slot. So you're always basically running inference. Now, during this time, the trainer is also training, which means you need to update the weights of the inference. And this is where the fun stuff happens, that you rather than actually, you figure out a way so that you pause the inference temporarily, do the weight update, and then you continue generating. And this actually has a huge impact on computational efficiency. And as you can see, the default way of doing off-policy RL, which is like what we call BP off policy, is substantially much more inefficient in terms of like the scaling tricks we got in the scale RL work. And what we have done is that we actually enabled pause and resume during wait updates, where the inference requests are not trained. And this is like a very important piece for us so as to squeeze out efficiency from our infrastructure. Now, one thing you notice is that the async RL would use stale infra, meaning the policy that generated the data may not be exactly the policy that is being trained right now. And this is commonly known as off-policy RL training. And a common way to deal with this is basically this thing called importance sampling. So the RL objective is to maximize the expected reward under the current policy, but we're sampling from an old policy. And what importance sampling does is this corrects for this by reweighting each sample by the ratio of the current policy's probability to the old policy's probability. So this is actually very simple to do. And now there are different variations and different things how people use this. And this brings me to this slide, that not always or all algorithms are doing so are created equal. And one thing I would say is, here I'm showing you some results where I guess things like, let's say some of these methods like the clipped importance sampling or CISPO is actually doing much better than other things like DAPO. But I guess the other thing I would mention is, even if, let's say, these things are comparable, one thing that the ScaleRL paper pointed out was that the asymmetric clipping thing in DAPO is actually extremely sensitive to hyperparameter tuning. And my claim generally is that hard-to-tune algorithms are just not worth it at larger scale. And the other thing is that any new hyperparameters that you add, they add actually one more knob to tune. So instead, a simple thing I follow is basically we should pick the simplest choice that works. For example, we should just drop KL regularization if it works. And I think that's what we do here at Periodic also. Now, the choice of method we have picked, which works well enough for us, is this thing called masked importance sampling reinforce. The idea is actually very straightforward. Even after, let's say, reducing all the train inference mismatch, things like, let's say, router replay or kernel fixes or a bunch of things, there are still a small number of tokens where the discrepancy between train and inference would be large. So usually this is like, let's say, less than 0.02%, like maybe even smaller. So what we do is simply mask these tokens away in the gradient update. And this simple trick is actually works pretty reliably. And we see that, so these results are shown for another communicated run, where we see that the discrepancy actually does not increase as we do more and more RL training. So this makes training extremely stable, which is, yeah, this basically makes it very easy to train for really long amounts of time. All right, so far I covered a bunch of things. What's next? So I guess one thing I'd say is, like, by focusing directly on advancing science, uh, actually different sets of machine learning infra and research questions will rise to prominence. So one thing we think a lot about is, let's say the LLM proposes a material synthesis experiment, then RL can connect it to verification, or RL can be used with verifications at different fidelity levels. For example, you can have these neural physics models that can give you a signal in minutes. This is very fast, but very approximate. And then you can use physics simulations that can take several minutes, sometimes even hours. This is more accurate, but like, I guess, still somewhat approximate. And then the final real signal is actually you try to synthesize this material in the lab, and then you get the ground truth signal from the experimental results itself. And this will take actually multiple hours. Now, in this example, basically simulations and physical laboratories as reward function are actually very high latency. Compare that to, let's say, the neural physics model or a typical reward model people use. Uh, and there's no way really around this, in the sense that many interesting questions in life aren't instantly answerable. So you will find a lot of basically domains or other questions where you would face this kind of thing. And one thing that is needed for this is that we need to produce async RL stacks that are actually resilient to very, very stale of policy samples, which is key for achieving key throughput. But the other thing which will also come into play is that we also have to worry about data efficiency again, because we can only do so many experiments in the lab. And it's not going to be at the scale of, let's say, math or code, where we can run, let's say, even hundreds of thousands of things or rollouts and get reward for any of them. That's not just true in this domain. And finally, basically, we start with the analysis step, but the real prize is the hypothesis step. And that is the holy grail for LLMs in science, which is like the question of, can an AI look at experimental results, synthesize what it's learned, and propose generally novel hypotheses? And not just interpolate from non-materials, but actually make some sort of creative leap. Like, what if it tried this unusual combination of elements at this temperature and something like that? And this is where I think RL gets really exciting. So right now, our models are mostly learning to, let's say, analyze data better. But the next step is training them to propose better experiments and to close the full loop autonomously. So the reward signal would be things like, let's say, if you propose, did your proposed recipe actually produce an interesting material? And other ways to think about this. All right, I think this is a good point to end my talk. So let me know if you have any questions. I think I would be available to answer some of them. Yeah.